Hello. In this video, we'll be reviewing scalars and vectors as they appear on the physics and math sections of the MCAT. To begin, let's introduce both scalars and vectors. Well, scalars are just numbers that have a value, which is often called a magnitude, but they don't have a direction. So you can think of scalars as just a number, like 5. 5 is a scalar. It just has a value. So is -10. These are both scalars. Examples in physics of scalars are things like distance, energy, speed. These things don't have a direction. It doesn't matter what direction you're moving in, it just matters what the quantity is. On the other hand, vectors are numbers that have both a magnitude, so a value, and a direction. So examples of this are displacement, force, velocity, and you may remember from physics that distance and displacement actually are different from each other. So if you're moving in a circle and you start at point A and you go all the way around and you end at point A, then your displacement is 0. Right? Because you start at the same position and you end at the same position. So that has a direction associated with it. The direction is how far away are you from your starting position. Here it turns out to be 0. The distance, on the other hand, that you've traveled is just the circumference, or how far you travel along the whole circle. So the distance is a non-zero value, but the displacement here is 0. And vectors and forces and velocities also have directions. So you can say in what direction is the velocity, what direction is the force. Next, let's get into some basics of vectors. So vectors are usually represented as an arrow in a plane. So here we have the xy plane, and a vector is just an arrow pointing to this point here, let's say. And so it has a direction, and that direction is often denoted by the angle that it makes with the x-axis. So that's the direction that it points. And then the magnitude is equal to the length of the vector. So again, the direction of the arrow pointing is the direction of the vector, and that's often given by this angle here. So this is the angle. And the magnitude, or the length of the arrow here, so how long the arrow is equal to the magnitude of the vector. And this plus or minus sign here is just a technicality, because if you had, let's say, if you had a vector that pointed in the negative direction, right, then you might say that the magnitude is negative, or that that the length is negative, but the magnitude of the vector is positive. For the MCAT, this isn't really important, but it's just something that you may have heard before. So whenever you're solving a problem on the MCAT, you can just say that the length of the arrow is equal to the magnitude of the vector. And again, to measure the magnitude of the vector, if you had a ruler, you could just use a ruler, but we'll see below how you can actually solve for the length of this vector. But before we do that, let's get into how you can add vectors together. So there are two main ways that you may see of how to add vectors together. The first that I'll present is called the tip-to-tail method. So this method is straightforward. You take, when you want to solve for a plus b, you take the tail of b. So the tip of a vector is where the arrow is. So where the arrowhead is, where this part of the arrow is. So the top part, where the arrow part is, that's called the tip. And this bottom part is called the tail. So what we do is we take the tail of b and we move it to the tip of A. And we make sure that we don't we don't rotate B at all. So we keep B exactly how it is. We just pick it up and we place it onto A, making sure it's pointing in the same direction it was before. And the resultant vector means, here it just means A plus B. So whenever you're doing vector addition, the resultant vector is just the vector you get when you add two others together. So the resultant vector is the arrow that points from the tail of A to the tip of B. So let's see an example of this. As we see below, we have a vector A in blue and a vector B in orange. Then the purple vector, which I'll draw on the right, is the resultant vector. So the way that we solve this is we take A, we leave it where it is. Then we take B and we move it. So as you can see, I've moved B along A so that its tail is on the tip of A. This dotted arrow is just left over, so you see that B used to be here, and all I've done was I just shifted it along A so that its tail is on the tip of A. And when I do that, I just connect this point here, which is the tail of A, and I draw an arrow from there to the tip of B, which is up here. So I just draw an arrow here, and that's the purple arrow. So this purple arrow is the resultant vector, which is A plus B. So that's how you would do the tip to tail method for vector addition. You can also do vector addition using the components of each of these vectors. In fact, this is called the components method of vector addition. And the way you do this is that given any vector v, we have x and y components, which are given by the following. We have an x component given here, which is called vx, and that's equal to the magnitude or the length of the vector, v, times the cosine of the angle, theta. And this x hat here, you may have learned it's called a unit vector, but it just points in the direction of x. So it just points directly to the right. So it just points directly to the right like this. And it has a length of 1. So this x hat here just gives us the direction of vx. And the magnitude of v gives us the length of vx once we multiply it by the cosine of theta. Similarly for vy, we have y hat, so it points in the up direction, and we have the length of v times the sine of theta. So a diagram of this is seen here. So the orange vector is our original vector v, and theta is the direction of v. So it's the angle that it makes with the x-axis. Then the vx is the x component of v. So if you just drew a dotted line from the tail of v until you got right underneath the tip of v, that would be vx. So it just hides completely underneath v. Similarly, if you wanted to draw vy, you just start where vx was, and you go up along v until you reach the tip of v, and that would be vy. And the lengths are given by these equations. So to do the components method, you just add, if you have two vectors, a and b, you just add the x components together, and then you add the y components together, and the sum of the x components gives you the x component of the resultant vector, and the sum of the y components gives you the y component of the resultant vector. And the hypotenuse is just calculated using the Pythagorean theorem. So the hypotenuse is just equal to the square root of all of the x components added together, and then you square them, plus all of the y components added together, squared. Once you take the square root, you get the magnitude of the resultant vector. And the direction, the angle, it can be computed as well. So let's see an example of this below. As an example, consider the same a and b that we had before. Now, I can make the x and y components obvious for these two vectors. So these dotted lines here, the blue dotted line on the x-axis is ax, and this y dotted line is ay. So these are the x and y components of a. Then for b, this dotted line here in orange is bx, and the dotted line moving up is by. Then, if we add a and b together, the way that we do that is we take ax and we move bx to the tip of ax. As you can see on the right here, we took bx from here and we just shifted it over until the tail of bx was on the tip of ax. And then these add together to form the x component of a plus b. And similarly, for the y components, we take ay, we leave it where it is, we move by so that the tail sits on the tip of ay, as we can see on the right here. And then, if we drew a new dotted line, which was the length of these two stacked on top of each other, that would be the y component of the resultant vector. So what we can see here is that we've drawn the exact same a plus b as we did for the tip to tail method, just using the component method now. And here, the x component of a plus b is the sum of the two x components of a and b. And the y component of a plus b is equal to ay plus by. So it's the sum of the two y components themselves. Next, let's look at how we can find the angle of a plus b now. So to find the angle, we have this v, and we have its x and y components. And this forms a right triangle, as we can see here. So this forms a right triangle. So we can use the rules that we know from trigonometry to solve for the angle. So as long as we know the x and y components, let's say, we can solve for the angle. You just have to know any of these two. It doesn't matter which two you know. For this example, I've just assumed that we know x and y. Assuming that, we can use SOHCAHTOA. So SOHCAHTOA says, what is the direction of v? Well, the tangent of this theta is equal to the length of the y component divided by the length of the x component. Then you can take the inverse tangent, which is just a function on your calculator. And when you do this, you find that the angle is equal to the inverse tangent, or the arctangent, of the length of the y component divided by the length of the x component. And that's how you would find the angle of a resultant vector given two of its lengths. Next, let's look at how we can subtract two vectors from each other. Subtracting two vectors from each other, we can use the two methods we used for vector addition above. So let's start with the tip to tail method. So for vector subtraction, it's very similar to vector addition. So we add these two vectors using our favorite method, whether it's tip to tail or component method. But this time, the subtracted vector, so the one with the minus, we make sure it has the opposite direction. So what I mean by the opposite direction is seen in this example here. So consider the same a and b vectors we've always been working with. And before, we moved b up to a, so the tail of b up to the tip of a, and we had it pointing upwards, like this. Now, for vector subtraction, we still move b up to the tip of a, but now we just flip it. So if you had b here, as I drew on the left, then the new b, you just draw a straight line down. And it has the same length of b, but it's in the exact opposite direction. So this orange line here, I would just flip b. And that's what the new b is for vector subtraction. So as we can see here on the right, if I wanted to subtract b from a, I take the old b, I move it up to the tip of a, and then I flip it. And when I flip it, this gives me negative b. So just like we did before with the tip to tail method, I then draw an arrow from the tail of a to the tip of what is now negative b. And when I do that, I get an arrow pointing down, given by this purple arrow, and that's the a minus b vector. So that's how you would use the tip to tail method. Now let's use the component method for vector subtraction. Using the component method, again, we draw these components of a and b as we had before. And now, what we did before was we had bx and we moved it to the tip of ax. And that was the new x component. Now, we take bx, we flip it in the other direction, so now it has a negative direction. We still move the tail to the tip of ax, but it's pointing in the opposite direction now, as you can see by the graph on the right. So this dotted blue line is still as it was before, but now bx points in the left direction, so we lose some length. Similarly, for the y direction, we keep ay where it is, but for by, we move by here up to the tip of ay, but we put it in the opposite direction, so it subtracts some length. And because by is greater in length than ay, we actually point below the x-axis. So as you can see here, I draw an arrow from the tail of ax to where these two arrows meet each other. So I draw an arrow to wherever the resultant y vector and x vector actually is. So here, it's at this point. So I draw an arrow to this orange point, and that gives me the resultant vector, which is the same one that we found above for the tip to tail method. So just to be clear, all I've done is I've left ax and ay the way it was, but now I have that, I'll draw it up here, I have that a minus b, the x component of it is equal to ax minus bx. And similarly, a minus b, the y component, is equal to ay minus by. So all I've done is I've taken the length of by and bx, and I've just made it negative. And then we add them the way we usually do. And wherever the new x and y components are, those are the x and y components of the resultant vector. And that's how you add and subtract vectors. Now, let's look at how you can multiply vectors. Firstly, let's see how you multiply vectors by scalars. So when you multiply a vector a by a scalar m, we are just increasing or decreasing the size of a. So here, let's say that we have a given by this orange vector. Then, let's say we have these x and y components as given by the blue dotted arrows, and we multiply a by 2. Then, all we do is we take each of these components, we make a copy of it, and we just put them tip to tail. So here, for a, I've literally just taken a, made a copy of it, and moved it up so that the tail of one a is on the tip of the other. And this is the new resultant vector. I just multiply it out, I just double it. Same for the x and y components. So for the x component, all I've done is I've taken AX and I've put another AX right in front of it. And for AY, I just put another AY right in front of it. And the reason I only use 2 vectors here is that we're multiplying by 2. If I multiplied by 3, let's say, then I would put 3 AXs next to each other and 3 AYs on top of each other. And then the resultant A would be 3 times stacked on top of each other. And if I had a negative instead, we would just flip all of the directions of all of these vectors. But regardless, all you do is you take each of the components and you multiply them by this number, whatever number you're dealing with. Here I used 2, but generally you can use m. And when you multiply a vector by m, which is a scalar, you get a new vector where each of its components are just multiplied by m. So that's how you would multiply a vector by a scalar. Now let's see how you would multiply vectors by other vectors. It turns out there are 2 ways of doing this. One way is called the dot product. And for the dot product, you multiply 2 vectors together, symbolized by this dot notation, and you get a scalar, which is just a number. So the formula for the dot product is given here, which I'll square in orange. So the dot product formula is you have these 2 vectors, and you dot them together, and the answer is just the magnitude of A, so the length of A, times the magnitude of B, times the cosine of theta, where theta here is the angle between A and B. So you just find the angle between A and B, and then you find the lengths of A and B, and you know the dot product. An example of this is work. So work is, an example of this is work. And work is the force dotted into the displacement that the work is done across. And we know that work is a scalar. Similarly, the second way to multiply vectors by vectors is called the cross product. Here, this is symbolized by this little x or cross notation. And what you say is one vector cross another vector is equal to a third vector. And the formula for this is A cross B is equal to, so I'll square this in orange. The formula for this is A cross B is equal to the magnitude of A times the magnitude of B times the sine of theta, where again, theta is the angle between A and B. So if you know the angle between these 2 vectors, and you know their lengths, you can compute their cross product. An example of this is torque. So we know that torque is the force cross the lever arm that this force acts at the end of. And torque is a vector because it has a direction. So it's the cross product of 2 vectors. And you may be wondering, there is no direction on the right side of this formula. So why is it a vector? Where is the direction of this third vector? Well, there's a very useful rule when finding the direction of the cross product, and it's called the right-hand rule. So let's use this stock image of a right hand as an example. We see that to compute the direction of the cross product, for A and B, we say take your right hand, make it into an open hand like this here, and then point your fingers in the direction of the vector A. So however it's drawn on your page, the direction of vector A is where your fingers point. Then rotate your hand so that your palm points in the direction of B. So here, B is actually pointing out of the screen. So it actually is pointing towards you. I can't really draw that, but this is my best interpretation. But point your fingers in the A direction of vector A. Point your palm. So rotate your hand so your palm is in the direction of B. And then wherever your hand is, stick your thumb out. And your thumb points in the direction of the new vector of A cross B. So since A cross B is a vector, it needs a direction. And its direction is given by the direction of your thumb. Then, the magnitude of A cross B is given by the formula that was on the previous slide. And here, a good way to think about this is that if you have A and B, you can actually form a plane, so like a sheet of paper, that these two vectors live on. So you can imagine a piece of paper given by this orange shaded region that A and B live on. So imagine this orange thing is a table, and A and B are just resting on that table. Then A cross B, the cross product of A and B, points in a perpendicular direction to the table. So we can either point up away from the table or down towards the table. Here, because of the directions of A and B, the cross product points up. So this cross product, it sits on the table and it's perpendicular, so at a right angle to the table, and it points directly upwards. So that's how you would find the direction of the cross product of two vectors. Finally, let's look at an example of computing both the dot product and the cross product. So as an example, let two vectors live in the xy plane as seen here. So we have A along the x-axis and B along the y-axis. And we have an angle theta separating them. You're given that AX is 4. So the x component of A is 4. And BY is equal to 5. So the y component of B is 5. Firstly, let's find AY, BX, and theta. Well, AY, since A is on the x-axis, AY is 0 because it has no y component because it's only on the x-axis. Similarly, BX is 0. So BY is the only component of B because B is on the y-axis. So BX is 0. And because these vectors lie on the x and y-axis, we see that theta is the angle between the x and y-axis, which is 90 degrees. So theta here is 90 degrees. So there's actually a right angle between A and B. Then let's compute A dot B and A cross B. So to start, let's compute A dot B. Well, remember that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle theta between A and B. But because A and B are just in the x and y directions respectively, we already know their magnitudes. We know their directions, or we know their lengths. So here, the length of A, since it only has one component, is just 4. We don't need to use the Pythagorean theorem of the x component and the y component to find the hypotenuse. So the magnitude of A is just the absolute value of 4. And the magnitude of B is just equal to the y component of B because it points only in the y direction. So this is the absolute value of 5. And theta here is 90 degrees. So we have the cosine of 90 degrees. So this is equal to 4 times 5 times cosine of 90 degrees. But if you know your trigonometry, or you plug this into a calculator, you'll see that the cosine of 90 degrees is 0. So the dot product of A and B here is 0. And that's because these two vectors are perpendicular to each other. And that's always true for vectors that have a angle separation of 90 degrees. Next, let's compute A cross B, so the cross product of these two vectors. Well, remember that the formula is A, the absolute value of A, or the magnitude of A, times the magnitude of B, times the sine of the angle between them. Then, this is equal to, next, let's compute the cross product of A and B. The way that we do this is, if you remember the formula, it's the absolute value of A, or the magnitude of A, times the magnitude of B, times the sine of the angle between these two vectors. Here, as we had above, we know that the magnitudes are the same as before. So, we have 4 times 5 times the sine of 90 degrees. But if you know your trigonometry, or you plug this into a calculator, the sine of 90 degrees is 1. So, A cross B is equal to 4 times 5 times 1, which is equal to 20. But remember, this isn't enough to answer what is the cross product. We also need to know the direction. So let's use the right-hand rule to find the direction of A cross B. To do this, we point our fingers in the direction of A. So point your fingers in the direction of A. You may have to turn to do this. Then, rotate your hand so that your palm is pointing in the direction of B. When you do this, you see that your thumb points up. So, here, since we're on this screen, the direction of A cross B points out of the screen. It points up towards you. So, the direction of A cross B is out of the page. And the way that we indicate that is by a circle with a dot in the middle of it. So this is the answer of A cross B. And if we wanted to indicate instead that it was pointing down into the page, which would be the case, say, if B pointed down instead of up, then we could use another symbol. So firstly, this symbol means out of the page, and this is often used on the MCAT, and this symbol means into the page. So the way to remember this is that if you imagine you had somebody shooting a bow and arrow, if the bow and arrow were coming out of, if the arrow were shot and it was coming out of the page towards you, all you would see was the tip of the arrow. So here, this little circle with a dot in the middle, you can imagine it's just the tip of an arrow coming right towards you. But if you had somebody shooting an arrow away from you or into the page, so down into the page, then what you would see is the arrow moving away from you. So you would see those 4 feathers on the end of the arrow moving away from you. And that's what this cross, you can imagine, means. So that's just one way of remembering this. But regardless, what we found is the dot product of A and B is 0, which is a scalar, and A cross B, the cross product between the two vectors, is 20, and the direction is out of the page. So it points towards you, out of the page. And this concludes this video covering vectors and scalars as they appear on the MCAT. Thank you.